second speaker, Marta Victoria from Department of Mechanical and Production for Engineering at Aarhus University. Marta obtained her bachelor and master degrees in aerospace engineering at the Technical University of Madrid in 2007, and then she obtained PhD at the Solar Energy Institute in 2014 in Madrid as well, and moved to Aarhus 2017 as a postdoc at the engineering department, and she was hired as assistant professor in 2019 and promoted to associate professor as right now in 2022, which is this year. So yeah, I lost tracking the year. She has a various interests in terms of work in energy in Europe, Denmark, and the world in terms of energy models. So I think it's good relationship to the Catherine talk in a way for renewable energy. And today she will show us about the alternative path to carbon neutrality. So stage is yours. And Marta, yes, yeah.
Thank you, Yuan. Could you confirm that you can hear me and see my presentation? Perfect. All right, then I will start. I want to talk today about alternative paths to carbon neutrality, and I want to do so by summarizing a few of the results that we got in a paper that we published recently, and this was the paper is called "The Speed of Technological Transformation Required in Europe to Achieve Different Climate Goals," and this was worked together with colleagues Elizabeth Seyen and Tom Brown at TU Berlin. Yeah, and you will get the links to the paper and the open version. And the paper is quite lengthy, so I want to try to use my time to focus on four key messages. The first one is that we need high time, space, and technology resolution. That's paramount when we want to investigate how to transition from today's system to a future sustainable system. The second message is that we cannot focus on 2050, but only on that, but also how to get there. So I want to quickly review the carbon budget and how that is key. My third message is that actually doing the transformation to limit warming to 1.5 degrees is not more expensive than limit that to 2 degrees, although I think it's significantly more challenging. I would like to be discussing that. And then I would like to use some time to discuss technologies for capturing and converting CO2 and what can we learn from the models regarding how much of those technologies do we need. So let's get started with the first point. The energy models that we used are based on the idea that in the future we might be able to get a sustainable system by producing our energy demands with solar, wind, hydro. But as you can see in these two images, the fluctuation patterns of solar on the left and wind on the right are totally different. And so are the fluctuations coming from hydro generation and even fluctuation coming from demand. And we might think, okay, how are we going to deal with those fluctuations? And one can think of, let's use storage so we can charge our storage when we have an excess of renewable energy and then discharge the storage when we have a deficit. So we are balancing in time. We can also think, let's extend our interconnection and let's use the network in this case to balance in space. So we are moving energy from regions where we have an excess to regions where we have a deficit. Or we can also think, well, let's electrify other sectors and benefit from that. So for instance, when we have an excess of renewable electricity, we can produce hydrogen and later convert that hydrogen back into electricity. And our point of view, or the research that we do, aims at including all of them, because the main point here is if we really want to understand how to combine these strategies, how much do we need of each of them, we need to co-optimize and to be able to have a system which we can see all of them at the same time. So to do that, we need to have high temporal resolution. Actually, we do modeling the uninterrupted hourly time stepping for a full year. And that's because the fluctuations from wind, solar, they are, as I was showing before, fundamentally different. So we need to make sure that we are seeing the needs for balancing in the intraday coming from solar, but also the fluctuation from wind that are more in the synoptic scale. So we have a week with a lot of wind followed by a week with low wind, roughly speaking. On top of that, we want to make sure that we go through, or we are modeling the balancing in the seasonal scale. So we have more energy need in the winter than in the summer. And we want to make sure that we want to cover that the system is safe for a very extreme situation. Typically, we have a week in winter with very low wind and solar generation, and we want to make sure that the system is going to withstand that extreme situation. So that's what we need: high resolution in time. We also need high resolution in Spain and in space, sorry. And in the models that we used, we try to use, we do optimization like what I'm showing. We represent how good is the wind and the solar resource. In this case, using 370 regions in Europe. And these maps already justify why we need the high resolution, because the quality of the resource is very different. So we want to make sure that we are capturing that. We need to go to the high resolution. Wind and energy requires that space resolution. On top of that, the third thing that we need to do is that we need to properly model not only the electricity sector, but also how we're going to supply heating demand, transport, land transport, but also, let's say, shipping or aviation. How we're going to supply the energy demand in the industry and fossil fuels or fuels used as a feedstock in the industry, and how it's going to work the complete carbon cycle. So that means that when we have this network, when we go into one of the nodes in the network, we need to have a proper representation of all the technologies to decide, let's see, how we want to supply heating. Do we want to use resistive heaters? Do we want to use heat pumps, gas boilers, combining and power? What would be the best option? But that also means that we need a detailed representation of also in space, what are the energy demands, for instance, in the industry. And that's something we have on the model. So where is the different industries in Europe today? Where are the cement plants? And what are the consumptions in terms of energy and in terms of output, in terms of CO2 emissions? How are those industries today? And how can they be in the future? And if they change, if we start, let's say, producing steel with direct reduced iron, where, when, and where are we going to have new demands for hydrogen? So combining all of this, we end up to being able to obtain solutions like these two coming from our recently submitted paper, in which we're able to plot on the left the best combination of technologies, so seeing a lot of wind on the north, a lot of solar, wind in blue, solar in the south. On the right, we are discussing what should be the ideal future hydrogen network, what should be the points where it's produced, and how this hydrogen needs to be transported through Europe. So I hope with these few slides, I've made the point that we need high time, space, and technology resolution if we want to see all this complexity coming from the model. So with this, I would like to, or before going down, I think it's also important to mention that we want to use open models and data. We do all our modeling on GitHub, and I think for this kind of topics is particularly relevant because we need to ensure transparency and reproducibility of our results. And with this, as I was saying, let's me jump into the second key message. We know, I think, but it's good to remember that there's roughly a linear relation between the cumulative CO2 emission and the temperature increase. And I have made a hand drawing of a figure coming from the IPCC just to highlight the most important parts. But the idea is that temperature increase is linearly related with cumulative emissions. The relation is roughly 0.5 degrees every 1,000 gigatons. So our historical emissions since 1850, we have emitted more than 2,000 gigatons. Hence, temperature has increased 1 degree. If we want to limit temperature increase to 1.5 degrees, there's only a limited amount of CO2 that we can allow, around 400 gigatons, and that's what we call carbon budget. And if we want to set the target in 2 degrees, then the carbon budget is a little larger. So what we did in that research is to try to answer what are the consequences for Europe to do the transition. So we model the transition from today to 2050 in 5 years steps, and all the different transition paths that we investigated have the same final point. So all of them achieve carbon neutrality by 2050, but they differ in that they use a different carbon budget. And then one question, of course, is how we allocate from the global budget, how we allocate a share to Europe. And we discussed that in the paper, but let's assume that we do that based on a per capita distribution. And then we'll cover this clear relation between temperature increase and the contribution that Europe will have for that temperature increase. And once we have this carbon budget, we just distribute it through the transition. So from 2020 to 2050. And as I was saying, all the transition paths end up getting to a neutral, carbon neutral system in 2050, but they differ in how much cumulative emissions they have through the whole transition. So how big is the area below the curves? And that's the second point I want to make. Not only 2050 is important, but how we get there. That's the transition, or the cumulative emission is what determines the contribution to the climate change. And now, what are the impacts of assuming different transition for the transformation of the system? So that's what we investigated on the paper. And we try to understand, okay, when will we need the different technologies? And I won't go into detail on the figure, but the idea is that what we learned, so the first thing that we learn is that in terms of technological transformation, the different transition paths require very similar transformation, but the main difference is when do we need them? So of course, if we aim at a lower temperature increase, we use a lower budget. That means that we need the transformation to happen earlier. And in particular, the 1.5 degrees scenario requires significant transformation in a very, very short term. And that's why it's being discussed in the global scientific community that the 1.5 scenario is extremely challenging. You can see things like, let me see if I can get the pointer. Yeah, but you can see things like the amount of, or when do we need electrolytic hydrogen to be something large and significant in Europe. And in the 1.5 scenario, we need that to already be something really big by 2030. And we do something similar with all the different technology, trying to understand when are we going to need them. On top of that, what we learned that it's kind of coincidental for all the different transition paths. Well, we see that we need a strong direct electrification. So we need heat pumps to electrify heating. We need electric vehicles to electrify the transport. And we also need indirect electrification. So we need the production of synthetic fuels, being hydrogen, being synthetic methane or synthetic oil, and use them to electrify the other sectors. And this we find that is cost optimal to support all of that through the deployment of renewable technologies. So in the different transition paths, we need to install a huge amount of renewables. What is particularly challenging for the 1.5 scenario is that they need to be installed really early in the transition. So 1.5 requires a dramatic expansion, in particular for the next 10, 15 years. We're talking about 400 gigawatts of wind and solar per year in Europe. That's roughly an order of magnitude higher than what we have done in the past. And that's dramatic ramp up needs to be not only for wind and solar, but also for hydrogen electrolysis, and also a little bit delay for heat pumps. So it's clear that 1.5 is going to be more challenging in terms that we need to move extremely fast. And that's what I was saying. The second point, it's important how we get to this carbon neutrality. All right, so we need to move faster for 1.5, but what about the cost? Is this going to be more expensive? So in the paper, we also discussed cumulative cost for the different transition paths. How much more expensive would be to attain 1.5 degrees instead of 2? And let me just mention one of the results. What we see is that 1.5. So you can see here the net present value of the system cost, the cumulative cost for the whole transition. 1.5 degree scenario is slightly more expensive than the others, let's say than 2%. But the cost differences are not that significant. In the text, we go into details investigating the impact the different assumption has on this comparison, and we particularly try different discount rates and different assumption on the social cost of carbon. So I will skip the complete description because it's kind of cumbersome. But I think what we learned, or our main learning from this exercise is, well, there is not a clear significant difference between 1.5 and 2 degrees. So from a pure economic point of view, we should be aiming at 1.5. And that's the message that I want to communicate. So limiting warming to 1.5 degrees is not more expensive than limiting to 2 degrees. We should, from a safety point of view, we should try to do that. The key challenge came more from the speed of transformation and speed of rollout of wind, solar, and electrolyzer and heat pumps that will be needed for the 1.5. And then I save the last part of the presentation to go more into details on the need for technologies for capturing and converting CO2, because that's what it's more related to the CO2 center. So what I want to try to present is what can we learn from our model regarding technologies for capturing and converting CO2. Let's see what are the options that the model has. So in every node in the network representing Europe, CO2 can be captured for any of these different processes. So it can be captured from a point source emission in the industry, all the cement, steel manufacturing. It can be captured from methane that is used to provide energy to the industry, from biomass used in the industry or used in combined heat and power. And we are using a quite conservative estimation of the potential of biomass that corresponds to 1,600 terawatts hour per year. CO2 can also be captured from direct capture technologies, also from methane using combined heat and power, and finally from hydrogen that has been produced via steam methane reforming, so what is called blue hydrogen. So we have a set of cost assumption and of course consumption of energy for the different technologies, and we let the model say, okay, which technologies will be cost optimal to use. And for the 1.5 degrees, this is kind of what we learn. So what we learn is first, model wants to, or is cost optimal to capture emission from the industry. And that makes a lot of sense because we need to capture that CO2 if we really want to. There's no other thing that we can do with that CO2, just use them to deplete the budget. But then what comes later? Well, later it decide to use capture CO2 from methane burnt in the industry and start using biomass either in the industry or in combined heat and power. And after that, it's where the models start using direct air capture. So we have already a first order of technologies that become more competitive and how they are selected for the very ambitious 1.5 degree scenario or transition path. And then all the CO2 that has been captured, how does the model wants to use it? So they are, yeah, sorry, before that, we don't see, there are two technologies that we don't see being part of the optimal solution. That's methane in combined heat and power, but that's also capturing CO2 from the production of hydrogen. So blue hydrogen from a system perspective, and we can discuss that more later, from a system perspective, we don't see that being part of the solution. That would be too expensive. And then as I was saying, what do we do with all this captured CO2? So we have three options in our model. CO2 can be sequestered underground. We assume 20 euros per ton of CO2. And we also assume a quite conservative potential for capturing CO2 in Europe, which corresponds to 200 megatons per year. And in the different regions, the model can also take CO2 combined with hydrogen and produce synthetic methane. And that will, of course, require that somewhere, when it's cost optimal, the corresponding hydrogen is produced so that we can end up having this methane. It can also use the capture CO2 to produce synthetic hydrocarbon using the Fischer traps that will also require to produce some hydrogen. And all of this will have a certain, of course, cost and a certain energy consumption or efficiency of the conversion. So with these three options, we let the model choose. And what do we see? Well, the first thing that the model likes to use is sequestering that underground. And that's, of course, based on this conservative, I mean, that's, of course, based on this set of assumptions. So we can later try to understand how robust is this result. But we can clearly see that this is the first step. And later, at a later step, it's gonna start using synthetic or start producing synthetic hydrocarbon via Fischer traps, and at a later point producing synthetic methane. So let's say this is for the 1.5 scenario that, as I mentioned, requires dramatically fast changes, but we can do the same with all the different scenarios and learn if the speed of transformation that we are requiring could be slower, or if we end up having more emissions, how robust are those things? And of course, again, you can see that we end up requiring the different technologies at different time steps, but most of the time, the order in which we are using them is quite robust. So there's always a willingness to capture things from the industry. Then as soon as we need more capture, use biomass, then later use methane. And then finally, if we need to really go to reduce the carbon budget that we use direct air capture. So as a final point, as I was saying, one of the main points that we learn is that storage, CO2 storage is, the model wants to do that, but I said that this is strongly impacted by our assumption. So one thing that we did is, okay, let me focus on this figure on the left. So what if we are wrong with our cost assumption of the CO2 storage? Because that's something that is still quite uncertain. What if we say that the cost is 2 orders of magnitude more expensive? Still, we are gonna, the result that we found is quite robust, because still the model would like to capture at least 120 megatons. What if the so we investigate the sensitivity to different cost assumptions, and then what if we end up having much cheaper storage solution, like another magnitude lower? So if we do that, we have cheaper cost storage, and at the same time we have an increase of potential relative to our reference scenario. So if we are in the super easy scenario in terms of CO2 storage, how much will the system will be willing to capture then, or to store? Then we will get to a scenario in which instead of the 200 megatons, we have 1.1 gigatons. So my point here is that how big is the role of the CO2 storage also depends on what is the final cost and potential that we can effectively develop. And I think that's the fact that the maximum that we'll be willing to be capturing is around 1.1 gigatons is also something very useful that we can learn from our models. So I would like to conclude here and just go through the 4 key messages. One is that we need this high time, space, and technology resolution if we really want to see where to produce energy, where to consume, what do we need to capture CO2. The second is that it's important. What is important actually is not only getting to carbon neutrality, but how smart are we on using our carbon budget. Limiting warming to 1.5 degrees is not more expensive than for 2 degrees, but it's more challenging in the required speed of the transformation. And we're going to need technologies for capturing and converting CO2. So still we need to understand better when do we need them and to what extent do we need each of them. And that's going to be strongly impacted by how they develop through the transition. So I will stop here and give back the word to Yuan. I'm looking forward to questions and discussion.
Thank you, Marta, for the nice presentation. The overview, how we can really take this path to the carbon neutrality in a bigger picture.